Okay, I'm recording. Okay, so this is your most basic capacitor. It's just literally two metal plates, and I can set them on a table or something, and I can change the plate separation. The plate area is pretty much fixed. They're just aluminum. They've got a little terminal on each one, and I could hook this up to a battery. This in and of itself wouldn't really do anything except shock me. Like, I can't really hook this into one of those little circuit boards. It's just too big and floppy, but it's a good thing for demonstration purposes. The capacitors that, let's see, the capacitors that go into a circuit, I ordered some, and typically they are changed into this form. They're in a cylinder, so there's still two parallel plates in there, but they're curved as concentric metal plates with a dielectric between them. And these are, I don't know if you can see, it's kind of blurry, but it tells me what the capacitance is on here. Also, another thing I learned when I was ordering capacitors to teach about capacitors is that some capacitors, you can plug them in either way. Like there's not a positive and a negative terminal. They work both ways, but those are really expensive. So I had to get polarized capacitors that have a positive and a negative terminal. So I have to look at it carefully. I probably have to turn on the lights to do that. Okay. But here's kind of a giant size capacitor situation that I wanted to show you. This thing is called a Whims Hurst machine. And what do I mean by concentric plates? Hopefully this will show a little bit what I mean by concentric. So this is a glass jar. I talked about this yesterday. It's called a Leyden jar, L-E-Y-D-E-N. And it's got metal on the outside, and it's got metal on the inside of the jar. And by concentric, I mean like, concentric means like a circle within a circle. That's what I mean by concentric. So there's like a circle within a circle here. And between the two circles is glass, and then it looks like a little bit of styrofoam. So there's dielectric between these metal plates inside and outside. So this is a capacitor on this side, and this is a capacitor on this side. Then what I have is I have two wheels. Oh my God. I'm knocking stuff over, people. Look out. I've got two wheels, and they actually rotate in opposite directions. I don't think you can really see that from your angle. Oh, there we go. Maybe you can. Okay, they rotate in opposite directions. And what they do is they charge the capacitors, and they charge the capacitors in opposite ways. And then I've got these metal handles that are connected to each capacitor. So instead of the capacitors discharging across the plates, the capacitors can actually discharge across each other. So I hope it's not too bright in here. We'll see what this looks like. Oh, and I gotta crank it the right way. Hang on. Guys, I had it working. It's supposed to spark. Nah. I'm sorry. I fixed it this morning. I had it going. In order for it to work, all of the pieces have to be kind of just so, because it's got little brushes that are picking up electrons and transferring them to one side of the capacitor. And then there's little teeth on this other part that are doing the opposite. And friction isn't right. Too loose. I'll give it one more shot, and then I'm going to give up. You hear it. I don't know if you can see it. Again, I'm willing to sacrifice my computer, my poor computer. Oh, sorry, buddy. She does not. You guys, one of the things that makes me so sad is that if we were in person, I'd be shocking myself with the Van de Graaff, be shocking you. It'd be so much fun. Okay, there it is. There we go. So that's an electric spark every so often. And again, if we were in person, then we'd have to stick stuff in there to see what would happen, right? I mean, obviously, you can't just have a spark without like playing with it, sticking your fingers in it and stuff like that. So, so here's a piece of paper. I'm just gonna stick a piece of paper between there. I'll try to hold it. Ooh, my computer. I don't know if you can see the sparks going through the paper, which is pretty cool. Another little device I have, I think I'm going to back it up just a little bit because I am getting flickering on my screen. And I'm pretty sure they won't give me another computer if I'm just reckless. They should. This isn't really anything different. It just kind of looks cool. This is a little plate, oopsie. This is a little plate and it's got little gaps in it. So it's kind of like a printed circuit board. This is metal and then there's a gap and I have it hooked up. So let's see if it'll work. You can see the sparks discharging through the gaps there, which is pretty cool. And I can give myself a shock, just like the old days. It's a lot more fun with an audience, though, I'm not going to lie. You can see it. Awesome. Okay, I'm going to pause my recording. Okay, perfect. Okay, so this is good because now I had a practice run. I've been making videos for AP Physics 1. Oh my gosh. Sometimes I have to do it like 4 times. It's the worst. Okay, anyway, here we go. Okay, so now I'm recording. We're in the Capacitor Lab, and we have a situation where I can, well, I'm going to discharge this. So it's running the light bulb. So let's start over. Okay, we have an uncharged capacitor. We have a battery. If I want to charge up the capacitor, I'm going to hook it up to the battery, and then I'm going to turn up the voltage. And we can see that the capacitor is pumping electrons off of the positive plate and putting them onto the negative plate. And if I turn up the voltage a little bit more, it pumps more electrons, putting more charge on the plates. A couple of things to notice. The top plate charge is given here in picocoulombs. The top plate charge and the bottom plate charge are the same because because charge is conserved. So if I remove one electron from the top, I put that charge on the bottom. There's no charge that just like magically appears from nowhere. This capacitor creates an electric field, and we studied the uniform electric field in previous sections of this unit. Okay, are we assuming there's an insulator between the plates? There can be an insulator between the plates, but there doesn't have to be one. In this case, it's just air. But if I put glass between the plates, then I would be able to put the plates closer together. And if I put the plates closer together, I'm actually able to store more charge. Now in this simulation, there's no spark jumping the gap, but we just saw on the Whims Hurst machine that you certainly could have it jump the gap, and we wouldn't want that if we're trying to store energy. Also, it's really not safe. Again, in guitar amplifiers, there are capacitors that will store, well, they'll have a voltage across them of like 300 volts, more than, because of the way that it's wired, it's more than the 120 that comes out of the wall. And so we want to be really careful when we have a charged capacitor because it can really injure humans. Okay, so now I've got this I've got this thing charged up, and now I'm going to detach it, and it's just sort of floating in space in my little imagination here. And if I pull the plates apart, I have to do work, right? The plates are also attracted to each other. So if I pull them apart, I do work. And when I do work, I want you guys to watch what happens to the stored energy. I do work to pull them apart, and the stored energy actually goes up. In fact, I'm going to put it back to where it was. Watch this. I've got voltage, and I'm going to check the voltage of my capacitor here. Okay, so the voltage is the same as what I had on the battery, 1.15 volts. And now I'm going to increase the plate separation and watch what happens to the voltage. The voltage goes way up because the work that I do to pull those plates apart is stored in the capacitor. And again, a capacitor is a way to store energy or store work. Yes, the plates are still charged even after it's detached from the battery, as long as it's insulated. So I am assuming that I've got this thing on like metal sticks or not metal, on wooden sticks or something that would be insulating. It's a little bit of an unrealistic, you know, it's just kind of floating in space in my simulation here, which maybe is not super realistic, but that's what we got. So, okay, so now I've got a charged capacitor. And again, in one of those, in one of these, let's go back here. In one of these circuit boards, you might have a capacitor, and then you might also have a switch or a gate that's telling when to charge the capacitor and when not to charge the capacitor. Again, we're getting a little bit outside the scope of how far we're going to get in this class, but just to give you the idea. So we've got a charged capacitor, so now what can I do with it? So if I were using it as a flash bulb, I could hook it up to a light, and then the light glows, but as the capacitor discharges, hopefully you saw how the light got dimmer and dimmer and dimmer because the voltage across the plates got less and the current decreased until it was 0. And now we're back to where we started. So I could hook up the capacitor to the battery, and I could charge it up, and then it could stay charged, and then I hook it up to a light bulb and I could discharge it. And as it discharges, the voltage decreases, and now the voltage is back down to 0. Okay.